shared the session, right? Like a VLSA demo session and digital PPT. Have you gone through that, everyone?
Yes, ma'am.
So,
Yes, ma'am.
did you have any doubts in the VLSA demo session? Like we have discussed what is the history of VLSA and what is the future of VLSA and what are the different fabrication technologies involved in it and the VLSA design flow, right? Whatever we are designing the IC manufacturing process, several steps are involved in that, right? So, did you have any doubts in that? So, what is the difference between ASIC and FPGA, SOC related things? What is the future? How the ICs, how we are going to store the data using AI technology involved to the VLSI? So, did you got clarity, everyone, on those session?
Yes,
So
ma'am.
if you have any doubts in the session, you can discuss with me. I can take the introduction here, but if I take a 1 day for introduction, it will be waste of time. So that's why I'm just directly moving to the digital logic design. That's why I shared the introduction video to you so that you can go through that and you will get the doubts. Okay, still anyone didn't attend, didn't seen that video, just go through that session so you will get overall things of VLSA, what is meant by VLSA and the manufacturing process and history and future scope. Okay, and I have shared the digital logic design PDF also, so that you can go through the digital PDF. You will get the things of combinational. Okay, so far you have read those things, right, in your graduation and all, so second year BTech and all. So that's why I just shared you before only to revise the concept, so that now we are taking some concepts related to the interview questions, right? So it is very easy to answer the questions and all, so that's why I shared you the questions and all. So yeah, so I think that's it. Anybody want to join still? Mm. Okay. Okay. Have you gone through the PDF like Boolean algebra and combinational sequential register, at least up to registers counters? So finest admissions we'll discuss whenever we are moving to the Verilog code for the finest admission. That time we can discuss those things. But today we will mainly concentrate. Today we'll mainly concentrate on. Just a second. Okay, today we'll mainly concentrate on the basic of digital logic design and combinational sequential registers, counters, and all the way of interview questions and all. So theoretically, we are not going to discuss the things theoretically. Just we'll focus on practically how we will face the interview questions. Okay, for different companies. If you go for service-based companies or product-based companies, okay, here there are some IITs also, IIT and IITs also, right? So we'll see how the different type of questions, all the questions we can't cover in 1.5 hour session. Okay, we'll discuss we'll cover entire topics of digital logic design today, and tomorrow we are going to discuss on static timing analysis and CMOS technology questions. Okay, from Monday onwards, Monday to Friday, I think Friday or Saturday we can extend 1 or 2 days. Okay, if we don't, if the time is not sufficient to discuss all the things, we can extend the session 1 or 2 days. That's not a problem. Okay, so these 2 days will be, today will be digital logic design, tomorrow will be ST and CMOS. From the Monday, we are going to discuss Verilog sessions. Okay, 1 day is for theory, and from day two onwards, we'll discuss on the practical sessions. Okay, for combinational, sequential, and finite state missions, memories 1 day, and projects. Okay, one protocol and one projects as we mentioned, right? These are the things we are going to discuss in this 1 week workshop. So if you are facing any doubts in the middle of the session, you can always ask your doubts. Okay, we can discuss your doubts. So make this session as more interactive. Okay, and we are going to discuss all the things in a real world manner. Okay, not theoretically. Mostly we'll focus on the practical things. Okay, so that's why explore yourself. If you have any doubts, please share your doubts. We can discuss your doubts, every doubts, and whatever the questions I am asking, please respond to the questions. Okay, so that I can understand your how you're thinking and what are the answers and all we can share. Okay, so this is a day 1 workshop. This workshop is a all-in-one workshop, like a RTL design workshop. RTL design in the sense register transfer level workshop. Okay, so in this mainly we are focusing on advanced digital logic design, means circuit designing and Verilog HDL. Okay, Verilog HDL is mostly important for the Verilog part, right? So all the things whatever we have from basic to the advanced level, we are merging all the things and mostly we'll discuss most of the practical things. Okay, so if you have more time, try to spend more time only this 1 week. If you spend maximum time in this workshop for assignments and all after the workshop classes, after the workshop sessions, so that you will get maximum things and you can learn very long within these 1 to 10 days, 1 week to 10 days. Okay, so that if you are interested for the job in the VLSA domain, you can take some other courses which are extension to this course. Okay, which are extension to this Verilog course. You can take some other courses after that. So what my suggestion is, whatever we are discussing, just please practice more. Okay, I know you are from college, you need to go to college and all. Okay, just spend 2 to 3 hours per day so that you will get you can complete Verilog course, entire course. Okay, maximum I will discuss the overall course only. Okay, so yeah, let's start with the day 1 workshop, digital logic design. Okay, so yeah, can you tell me why we are using digital? Okay, let me ask few questions. Okay, so what is the fabrication technology we are using in our VLSI? What is the fabrication technology we are using in our VLSI nowadays?
Ma'am, 180 nanometers.
One
180 nanometers, ma'am.
180 nanometer. Okay, is it correct? Anyone?
Is CMOS technology. Up to 45 nanometers, they are using practically. Up to 2 nanometers also. Up to 3 nanometers,
Ma'am,
it is possible.
Okay.
now
Okay.
we have gone up to 10 nanometers as well.
6 nanometer.
Okay. Okay, so present we are using as you told that CMOS. CMOS is a older version, the transistor, like up to 24 nanometer like that. So we are reducing the transistor year wise, day by day. So present we are using 6 to 5 nanometer technology. Okay. Moreover, we are going to meet 1 nanometer technology in coming years. Okay, maybe in 10 to 20 years we are going to meet 1 nanometer technology. Okay, so present whatever nanometer, very nano thin wire technology we are using in the fabrication. Okay, we have seen CMOS technology, FinFET technology, GAFET, MACFET. Okay, these are the different internal things at the physical design, the hardware which we are using in the IC fabrication. Okay, moreover, we are using the silicon material, right, which is a good semiconductor material for the IC manufacturing. So silicon is the best material for that. So yeah. Okay, next question is, what is the difference between ASIC chip and the FPGA?
Ma'am, ASIC chip is application specific. It's a more extensive chip, while FPGA is a programmable chip. which has muxes in it, and we can program it to drive a certain application. And it's also a low power chip, FPGA, while ASIC can be used in high power chips as well.
Okay, good. Okay. Any other answers?
ASIC is
And
application
FPGA
oriented,
is
and
just time.
FPGA can be used for various things like
FPGA used
verification
to for
on.
testing.
Okay. So ASIC chips are nothing but the permanent chips, whereas FPGA chips are the reprogrammable. Okay, like free field programmable gate array, as the name says. ASICs are the application specific integrated circuit. Okay, those are the permanent chips like our processors, wherever we are using in our laptops, mobile phones, and all. So once we dump the hardware, once we dump the RTL design into the hardware silicon, we cannot reprogram it again and again. Okay, those are the permanent and one-time configurable. Okay, we cannot change its functionality or operation once it got dumped. Okay, but FPGAs are not nothing but reprogrammable. It is like a ready-made chip. Okay, we can easily buy, as you are the students, we you can easily buy the FPGA chip and you can use in your projects. Different projects you can do with your FPGAs. Okay, so those are like a reprogrammable, which are used for low power applications and all. um yeah, this is what briefly about the ASIC and the FPGA. Okay, and next thing is so what is the different steps involved in the VLSI design flow? What are the
Ma'am,
different
it
steps
starts
involved in the design flow? Yeah, tell.
It starts with specification, then we go to architecture and behavioral design, then we go to RTL coding. We verify the RTL code, and if any bugs are there, then we again code it. Then there is synthesis and gate level simulation, and then we floor plan it and we do the timing analysis, and then we design the layout, and it goes to GDS too.
Okay, okay, good. Any other answers?
System specification and architecture design, like what and all the architecture, what and all the things we require from the market. We do take all the intakes from the market, and then functional designing, then logic designing, and fabrication, packing, testing, RTL
Okay.
coding.
Okay, okay. So you understood what is the difference between front-end VLSA domain and the back-end VLSA domain. So what are the different teams involved, and what are the different subdomains involved in the front-end and back-end? Okay, what is the difference between RTL design verification and physical design? You come to know all the things, right? So okay, that will be sufficient. So yeah. Today we are going to start the digital logic design. Okay, why mainly we are using digital logic design means we are focusing the VLSA digital VLSA, not analog VLSA, right? We have both analog VLSA design and the digital VLSA design, but we are in the present the world is in the era of digital. Okay, mostly all the things involved with the digital. Okay, that's why we are mainly focusing on the digital things, digital VLSA, digital IC manufacturing things and all. So for that purpose, whether you are going for the physical design, okay, back end process or front end design process, everything for anything, digital logic design is the basic thing. Okay, so you need to know the about the depth of digital logic design, and it is very important for the interview purpose. Okay, if you are if you are facing any interview, the first will be the general entrance test will be there, right? So for the entrance test, the most questions asked from the digital logic design, CMOS, and your analytical things and all, logical aptitude questions are these things. Okay, so digital electronics is also one of very important thing for the freshers, okay, to enter into the VLSA domain. Not only for the entrance test, in the technical round, okay, there will be very tricky questions will be asked by the panel. Okay, so like first round or second round. Okay, so digital is very important. You need to focus these tricky questions. Okay, mostly you are from IIT and IT means mostly product based companies will take very complex questions only. Okay, so for that purpose today we'll see some of the questions. So first we are going to discuss these things from basic. We'll start from basic to advanced level. Okay, so conversions, you know how to convert one decimal to binary, like that. And about the Boolean algebra, okay, we'll do few things. Just we'll touch every topic on the questions, and detailedly I will give you the some of the assignments. Okay, you can do the assignments so that you will get a overall things of every concept. Okay, and then combinational logic circuit, different problem statements we are going to see for the combinational logic circuit. And for the gates, related to the gates and related to the multiplexers. Okay, so encoders, decoders, everything we are going to discuss these things regarding to the flip-flops, latches. Okay, timing waveforms, how to draw the timing waveforms for the latches and flip-flops. And for the registers, okay, different type of registers, how to generate the register circuit diagram and all, like frequency divider concepts. Okay, and then the counters. Okay, so today is up to counters. Okay, we cannot discuss more than that within the time. So today is up to the counters. I think up to counters also we can't discuss. Yeah, finite state missions and all we'll discuss at the Verilog time. Okay. Okay, my first question is, okay, this is very interactive session, so you need to answer the question. Okay, that's why I already shared you 2 days before only to revise all the concepts, right? So we'll discuss both theory, we'll discuss, and also the technical wise also. Okay, can you tell me how to convert 7CF to the hexadecimal value to the decimal value?
Ma'am, we can
Can
simply
anyone?
expand it to ma'am, we can simply expand it into binary of 4 bits.
Okay.
Ma'am, your screen is not visible.
Screen is not visible.
16 power 0, 16 power 1, 16 power 2.
Screen is visible.
Yeah, ma'am, visible.
Yes, ma'am. Yes, ma'am.
Okay. Yeah. So first topic is the conversion topic, right? Have we already seen the conversion topic? Yes, tell. So how can we convert that hexadecimal value to the decimal value?
These two significant differences like 16 power 0
So
and all of
everything,
the 16 power 1.
yeah. So everything we need to take in terms of 16, base 16, right? Hexadecimal in the sense base 16. So converting to decimal means 16 power. First we need to take a 16 power 0 into what is the F? F is nothing but 15. So 15 plus what is the C? C means 12. 16 power 1 into 12 plus 16 power 2 into 7. 16 power 2 into 7. So if you calculate this thing, 16 power 0 is nothing but 1. 1 into 15 is nothing but 15. 16 into 12 is some value around 192, I think. And this is around some value 1791. So if you add this value, you will get the hexadecimal to the decimal value. Like that, if you want to convert octal to the decimal, you just need to multiply with 8. Binary to the decimal, the base value is the 2. Like that, you can convert one value to the another value. Okay, so like that, reverse, like a decimal to octal conversion, decimal to hexadecimal, decimal to binary conversion. Okay, that means dividing with the value. Okay, dividing, that mean here we need to use, suppose decimal to binary means divide with some other value. Decimal to octal means you need to divide that value with the octal 7 to 5. Hexadecimal means FA 2. So 16 we need to divide with that value so that we can convert into the decimal value. Okay, so decimal to binary or octal something. Okay, so next thing is convert 101011, which is a binary value, to the decimal value. So how can we convert this value?
Ma'am, we can use the same concept. We can use 1 into 2 to the power 0 plus 1 into 2 to the power 1, and it will go up to the last MSB.
Okay, so same like this only, same value. So 1 into 2 to the power 0 plus 1 into 2 to the power 1 plus 1 into 0 into 2 to the power 2 plus, like that. If you convert, we'll get the decimal value. Okay, so that is one type of conversion. Next, these are like a base 2, base 10, base 16. This is also base 10. Okay, but if you see here, this is the base 3. This value is related to the base 3, and I want to convert that base 3 value to the base 9 value. So how can we convert the base 3 value to the base 9?
Ma'am, we can make groups of 2.
Okay.
Can make the groups of 2 and then go from right to left, ma'am. Like groups of 2 and make go from right to left, ma'am.
3 in the sense we can make a group of 2. As we seen octal in the sense group of 3. Like that, 2 in the sense 2 power 3 in the sense within the 4. Okay, which is nothing but 2 power 2. Okay, n value is 2. So we can group with the 2 values like this. So here only one value left. So we can put 0. Okay. So base 9. Base 9 means how many values will be there? How many values will be there? There will be 9 different values from 0 to 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. So there will be these different number of values. Okay. So what will be the value for these? If you take in 3, okay, so what will be the value for these? 3 in the sense, base 3 in the sense will have only 4 number of combinations, 0, 0, 0, 1, 0, 2, 0, 3. So these values will have, okay, that means 0, 0, sorry, 0, 1, 1, 0, 1, 1. So like this, if you put here 0, 0, 0, 1, 1, 0, or i- 0, 2, again 1, 0, 3 means these 3 combinations will be there. Again 3 in the sense 1, 1, 1, 2, 0, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. Next 2, 0, 2, 1, 2, 2. Okay, these are related values for these. Okay, did you understood everyone? Like this only will take every base, right? Base 3 and base 9 will take like this. Here this value and this value, this value. So what is the value here? 2, 2. 2, 2 in the sense 0, 1. So here we'll get the value as 2, 2 in the sense 0, 1
8,
and
ma'am.
1, 1
Can
means
you,
Tell me
8.
just like whether it
can
is
you
two
explain
bit
it
or three.
another time?
Hello? Yeah, yeah.
Can you tell
Can
me
you
like
tell?
whether it is 2 bit or 3 bits? See,
We
when
need
it
to
comes
take, yeah, tell.
when it comes to base 8, it will be 0 to 7. So it is 2 to the power of 3. So 8 possible combinations will be there from 0, 0 to triple 1.
Okay, but here base 3 in the sense there will be base 3 in the sense will take only within the 4. Okay, so 2 to the 2 power 2 is nothing but base 4, right?
Yes.
So here we'll have two number of combinations. 2 means we need to divide entire value into the 2 number of combinations. Okay, if you divide entire combinations with the 2 number of values, suppose if you see here, there is a 2, 2. So what is the value related to 2, 2? Here we have the value 2, 2. So what is the value related to this 8? So here we'll get the 8. 1, 1. Where we have 1, 1, 1, 1 in the sense 4. So here we'll get the value as a 4. And next 2, 1. 2 1 in the sense this one 7 7 so here we'll get the 7 value. Okay, did you understood? Wait, I will show you clearly. I'm just taking this value. Okay, can you check now? So previously I have written, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8. So for base 9, this is for base 9, we'll have different 9 number of values. Okay, for base 3, we'll have 3 different values 0, 1, 2. Okay, so 0, 0, 0, 0, 1, 0, 2. I am considering here again 1, 0, 1, 1, 1, 2. Again here 2, 0, 2, 1, 2, 2. This is how we need to consider for base 3. Okay, if you see base 4, 0, 1, 0, 2, 0, 3 up to like this. Okay, 1, 1, 1, 0, 1, 1, 1, 2, 1, 3, 2, 0, 2, 1, 2, 2, 2, 3. This is for base 2. This is for base 3. Okay, what we have given, what they have given here, this is the base 3 value. These are the base 3 values. We need to convert these base 3 values into base 9 value. So first, what is the value here? 22. 22 in the sense 8. So first for 2 2 we are taking as a 8. Next one is 1 1. 1 1 in the sense 4. So here we'll get the value 4. Next 1 2. 2 1. Next 2 1 in the sense 7. 7 value will get. Next 2 2. 2 2 means again 8. Next 1 2. 1 2 in the sense 5. Next 1 0. 1 0 in the sense 3. Next here no value is there. You can simply put as a 0. So 1 1 is there. 1 1 means 4 again. 0 2 means 2. So this is the value we can convert base 3 into base 9. Okay. You know decimal values, right? Decimal values means we'll have 0 to 9 different values according to your octal, according to your hexa, according to your binary number. We'll convert a decimal to binary like that. Okay. Same as base 3 means we'll have 3 different values. So see here, base 3 in the sense you got only between 0, 1, 2. If it is binary, they will give only between 1 0 1 0 1 0 like this. Okay, so base 3 means between 3 numbers only they have given. Okay, so according to those 3 numbers, base 3 in the sense within the 2 power 2 equal to 4, within the range of 4. So we are taking as a 2 2. Okay, we are dividing every entire digits into the 2 2 digit. Okay, so we are converting into the base 9 by taking this table. Same as hexadecimal to decimal converter, octal to whatever we are taking, all conversions same. Did you all understood, everyone? Clear with the question?
Yeah, ma'am. Ma'am, for base 3 it is clear, ma'am. If they given base 5 to base 9, at that time what would we do, ma'am?
Base 5 means how many number of combinations in base 5 in the sense 2 power 3.
3
2 power 3
combinations.
is nothing but 8. So you need to convert all
Yes,
the
ma'am.
digits into 3 3. You need to take 3 3 and you can take the conversion table here base 3, base 5. Okay, base 5 in the sense will have 0 to 4 different values. 0 to 4 you can take the value. Accordingly you can convert. Okay. So everyone understood up to here?
Yes, ma'am.
Okay, next question. How can we implement the expression f is equal to a bar plus b of c plus f bar plus de using only NAND gates. Okay, we know how to convert the Boolean expressions. Okay, we did by using the K maps we have converted, and Boolean expressions using SOP, POS we have taken. Okay, different examples we have seen how to implement using NOR gate and NAND gate. If you want to implement using NOR gate, we need to convert into the addition format. Okay, so here we have a different multiplication format here, right? So if you want to convert into the NOR gate, we need to convert this multiplication into plus. This multiplication into plus. That means for every what we tell, every arithmetic operator should be the plus only between every variables. Okay, but here they are telling as a NAND gate. NAND gate in the sense for every arithmetic value, arithmetic sign, we should convert into the multiplication. Okay, so it will become like a NAND converter. Okay, so how can we draw this into the NAND? So F is equal to A bar plus B into C plus F bar plus DE. So how we can convert into NAND? We need to take into a multiplication. Okay, so first you do A bar into C, A bar into C plus B into C plus F bar plus DE. Okay, so what is the main thing here we need to do? We need to convert this plus, whatever the plus we have, we need to convert this plus into multiplication. Okay, so what can we do for that? We have two things. A plus B whole bar equal to, can you tell me what is this output? De Morgan law.
A bar into B bar.
A bar into B bar. So if you want to convert to the NAND gate, you need to use this formula. If you want to convert into the NOR gate, so you need to use this formula. A into B whole bar equal to A bar plus B bar. Okay, but here we need to convert into NAND. So using first one. Okay, so for that, what can we do? A plus B whole bar is nothing but A bar into B bar, but we don't have any whole bar here, right? So another expression is A double bar is nothing but A, right? So we can put this double bar here. Double bar in the sense no, not same value. Okay, we can cancel out the double bar. So I am taking two bars here, double bar. Okay, so now what can I do here? With one bar, I can take as a this one as a plus B whole bar, only one bar. Okay, so A plus B whole bar in the sense A bar into B bar, right? So how can we convert everything? A bar into C. For this we'll get a whole bar. B into C. F double bar into DE into bar. Okay, so you understood this point, right? So we'll get another bar here. Okay, so here A bar C whole bar, that means A plus B whole bar in the sense here A bar into B bar into C bar into D bar, like that. A plus B, B plus C plus D whole bar is nothing but A bar into B bar into C bar into D bar. Okay, so in that format we have taken. If you draw the output diagram, you will get the NAND gate operation. Okay, now if you look into here,